Hello and welcome to this What's New video for OrcaFlex 11. In the next few minutes I'm going to show you a few of the key new features in the latest version of the program. On the screen now you'll see the topics we're going to cover in this video. This is not a full list of what's new, so be sure to check out the documentation for a comprehensive rundown. You can access this in the normal manner from the Help menu within OrcaFlex or from the documentation page of our website. Okay, without further ado, let's look at the headline feature for this version, Diffraction. We've implemented Diffraction as a separate executable called OrcaWave. When you first open OrcaWave, you'll see that the user interface is much simpler than OrcaFlex, with everything taking place across a number of pages inside a single window. OrcaWave can support both first-order and second-order calculations, single and multi-body analysis, and it can generate sea-state RAOs. The methods of data input are very familiar in look and feel. For example, the wave periods and headings can be input directly or easily pasted from external sources. The Bodies page is where we define our mesh. You can see the ability to select multiple bodies here as well. We haven't implemented any meshing functionality within the program. Instead, the user needs to import a panel mesh file of either WAMET GDF, Aqua DAT, Hydrostar HST, CSAM FEM or Nemo DAT format. Once we've imported a mesh, it can be viewed and navigated. And again, the look and feel of the mesh view page should be very familiar to OrcaFlex users. Once we've reviewed our validation report, the diffraction analysis can then be run. When the analysis is complete, we're presented with a new graphs page which shows the results in the form of plots for each degree of freedom, and a new tables page which has sets of tables for all the requested data, such as the load RAOs and displacement RAOs. This data can be copied and pasted, exported to Excel from the right mouse button, but when we save the file, this will create a new .owr file, or OrcaWave results file, which we can then import into OrcaFlex. So if we move over to OrcaFlex, which was open here in the background, and if we open the vessel type data form, we can now go to the import button and select the newly created OWR file. Note that we have an option here to clear any existing data, which can be very useful for ensuring there is no stray data left over from the previous vessel type. Once imported, you'll see that the mesh has also been imported as a set of edges and vertices on the drawing page. This is an option we've made available in OrcaFlex in version 11, even if you aren't importing data from OrcaWave. And as we can see in the wireframe view, we have that panel mesh now imported. A significant part of our development work on OrcaWave has been on testing and validating the code. WAMET has been our primary source of comparison, and we will shortly be publishing a validation report to back up the software. This will be found on the validation page of our website. We're very proud of our first venture into the world of diffraction, but as with any significant software development, there are improvements we can make. We are already working on a number of things like, for example, providing iterative solvers as an alternative to the existing direct matrix solvers. You can expect to see many improvements to OrcaWave in the next release. Although, as previously mentioned, OrcaWave is a separate executable, it's important to note that it is bundled and licensed as part of OrcaFlex, and at the moment at least, it is not available as a standalone product. We hope you enjoy using OrcaWave and find it a useful addition to OrcaFlex. We also look forward to hearing your feedback so that we can continue to develop it in a way that is relevant to you, the user. For the next part of this video, we're going to look at enhancements we've made to the Turbine object. We introduced the turbine object as part of version 10.3, designed for modelling horizontal axis wind turbines and allowing for the first time a fully coupled wind turbine analysis without the need to interface with FAST. As with this year's introduction of diffraction, there were a number of features for the turbine which we weren't able to include in the first development cycle, and these have been introduced in version 11. The first of these enhancements is tower influence modelling. This is the phenomenon where the wind field experienced by the rotor is influenced by the tower that is downwind of it and is known as the tower dam effect. It is necessary to associate the turbine with a tower, and this is done by choosing from one of two tower influence models on the new tower page in the turbine data form. Both of these models are based on potential theory. The default setting is none, and when we select one of the other two options, we are provided with some new data input forms for the tower connections and the tower profiles. Once we have this data defined, on the drawing page there is a new option which allows you to draw the tower influence model in both the wireframe view and the shaded graphics view. We were aware that this was a desirable feature when the turbine object was first introduced, and are pleased to be able to offer it now. The next turbine enhancement is individual blade pitch control. After the introduction of the turbine object, a number of users requested the ability to individually set the pitch for each blade. And as a great example of our ability to react to customer requests, this feature is now included. By default, the pitch control mode on the blades page of the turbine data form is set to common, meaning one value will set the pitch for all blades. If the pitch control mode is changed to individual, the user can then set each blade pitch angle individually. The final turbine enhancement we will look at now is slave connections. In version 10.3, slave connections to a turbine were always connected to the hub. This has now been changed to allow connection to an individual blade at any arc length. This can be useful for a number of reasons. For example, to simulate rotor imbalance from ice buildup or blade manufacturing defects, as a means of applying externally calculated loads, or, as in this example, to enable the modelling of installation scenarios such as the lifting of an individual blade. Here you can see two lifting slings attached directly to the blade. We will now take a look at a number of enhancements to the line object. The first of these is the line reset drawing. In previous versions of the program, lines drawn in the reset state haven't recognised any interaction with the seabed. This is known as the quick catenary algorithm. Most OrcaFlex users will be familiar with the type of view seen here. Note we're in the reset state and this line is hanging below the seabed. The line also includes some buoyancy modules modelled as line attachments, and if we run statics we will see the line form a lazy wave profile. Resetting the model and going to the general data form, we can see a new page called Reset. This provides options for how lines are drawn in the reset state. Quick applies the quick statics method, and as with previous versions of the program, this doesn't account for seabed interaction or buoyancy, and is the method you can see on the screen at the moment. Analytic catenary uses the analytic catenary method for all users of this particular model, and according to preference will follow the user preferences, and I'll show you how to set those in a moment. If we change to the analytic catenary method, we will see the view immediately change, and the line now sits on the seabed and the lazy wave profile has been drawn, even though this model is still in the reset state. Note that the selection here doesn't influence the calculation at all, just the way the lines are drawn before the calculation starts. And just to show you how to set the user preferences for this, if you go to Tools and Preferences, there is now a page called Reset, and this is where you select your user preference between analytic catenary and the quick method. The next line enhancement we will look at is slug flow drawing. It has long been possible to model slug flow in OrcaFlex, but it has never been easy to visualize. This has now changed with an option on the drawing page of the line data form to draw slug flow. This applies to both wireframe and shaded graphics views, as can be seen from this model on the screen. We will now look at some improvements to the general user interface. The first of these is vessel and 6D buoy origin drawing. We will look first of all at the new options for drawing origins in the 6D buoy object. If we insert a new 6D buoy into this model, it is of course the lumped buoy type by default, and you will see a blue cross at the centre. This represents the centre of volume of the buoy. If we open the data form, go to the Properties page, and change one of the coordinates of that centre of volume, you will see the blue cross move, and now we have a second cross visible which represents the centre of mass of the buoy. And if we then go and adjust the centre of mass, you will see the red cross moving as well. I'll just reset both of those back to the centre and then convert to the spar buoy type. Now we see the red cross, the centre of mass, is placed at the bottom of the cylinder, which is the default position. The centre of volume is at the centre of this cylinder. For a spar buoy type, the centre of volume is calculated automatically based on the geometry, and we can demonstrate this by adding a second cylinder, and at the moment that blue cross is now at the centre of that stack of cylinders. If we just change the outer diameter of one of those cylinders, you should see the blue cross move. Moving now to the vessel object. In this vessel on the screen you can see a blue cross which represents the origin of the diffraction data. If the origins of the diffraction data vary, such as REOs, phases, etc., then you will simply see multiple crosses of this colour. Now if we open the vessel type data form and modify the centre of gravity of the vessel, then we see a red cross appear, and this red cross represents the centre of gravity. In fact, there are 6 different origin colours available on the vessel data form. On a new page called Origin Drawing. As an example, we'll go in and modify the current load origin positions. Again, we have to go back to the vessel type data and go to the current page and modify one of the coordinates there. Although we've modified that origin position, we haven't actually seen a yellow cross appear as we would expect. But don't worry, we just need to select the current load as an included effect on the vessel data form before that origin will appear. So going back to the vessel data form on the calculation page and selecting current load, we now see that yellow cross appear. The next user interface enhancement we'll look at is panel mesh file drawing. As part of the OrcaWave development, we implemented code to allow the import of panel meshes. It was clear that this would be a nice feature to carry over into OrcaFlex in order to allow a mesh to form the basis of a wireframe drawing. Here we can see the new Import Wireframe option, which allows us to select a mesh file from a number of sources, including WAMIT, Aqua, Hydrostar, CSAM, and Nemo. Multi-body mesh files for Aqua and Hydrostar are supported, as is the ability to discriminate between wet and dry panels for Aqua mesh files. As well as unit conversion, we need to specify symmetry at this point if the mesh file isn't a full model. As an example, we will import a GDF file for a semi-submersible which has symmetry in both XZ and YZ planes. Without specifying symmetry, we only import a quarter of the model. If we go back and apply the necessary symmetry, then we can see the full model as expected. Interestingly, if we move to the shaded graphics mode, we get a very unhelpful rendering of this semi-submersible. OrcaFlex has attempted to find the smallest convex shape containing the wireframe, and in this case it's really of no use at all. So what can you do for the shaded graphics mode? If you have the mesh in a CAD package, you can of course export it to an OBJ file and use that here instead. Alternatively, we have also enabled the import of a panel mesh file for shaded graphics, which we'll do now. Note that again we have options for symmetry, which body, if it's a multi-body input, and whether or not we want to import dry panels. Again, we need to specify the symmetry in this case. And here we see the body imported as we would expect. We will now take a look at an improvement to the constraint object, hysteretic stiffness. It is now possible to apply hysteresis to a constraint stiffness profile. This can be very useful for modelling friction-like phenomena such as breakout friction in a turret mooring. In the example we see here, a constraint has a single degree of freedom with an associated variable stiffness. This translational stiffness profile varies linearly from 0 to 10 kilonewtons over a displacement of 0 to 1 meter, and then remains constant thereafter. Attached to the constraint is a winch, which is set to pull the constraint a total distance of 5 meters before being released. And finally, we have a 3D buoy connected to the constraint, which has some mass in order to give the system inertia. Once the deflection reaches 1 meter, the winch tension peaks at 10 kilonewtons, the specified breakout deflection force. Then, when the winch releases, the constraint stiffness is no longer opposed and acts to reduce the deflection. Without hysteresis, the system returns to 0 deflection, as we can see here. But if we reset the model, enable hysteresis on the variable data form, and then rerun, we will see the constraint instead settle on a new position. We will now turn our attention to the inclusion of wind drag loading on 6D buoys. In previous versions, wind loading could only be applied to vessels, lines and 6D buoy wings. Version 11 adds to that list by enabling wind drag loading on 6D buoys. The drag load is calculated using the existing drag area and drag coefficient data on the 6D buoy data form, and on the wind page of the environment data form there is a new option called Include Wind Loads on 6D buoys. When loading old data files, this option is unchecked to reproduce the original behaviour of the program, but for new models this will be checked by default. In this example we have 2 stiff lines with a 0 mass 6D buoy at the top of each. One of the buoys has a 0 drag coefficient, while the other has a drag coefficient of 1.2. And just going back to the environment data form, we can see that the new option to include wind loads on 6D buoys is checked, as well as a constant wind speed being defined of 25 meters per second. And when we run statics, we can see how the buoy that attracts drag is pushed across by the wind. We also now have some additions to the available wind types in OrcaFlex. In a similar way to waves, you can now define your own wind specification, either through a user-defined spectrum or through user-specified components. In addition, the ESDU spectrum is now available as a built-in option, allowing for the simulation of tropical cyclone conditions. The final part of this What's New video will focus on enhancements to the vessel object. Previous versions of the program only allowed vessel current and wind load coefficients for 3 degrees of freedom, i.e. surge, sway and yaw. This has now been extended to allow coefficients for heave, roll and pitch also, i.e. 6 degrees of freedom. It has been possible for a number of years for vessels to model the disturbance of the sea state around them using sea state RAOs. However, we haven't until now had an efficient way of querying disturbance results at specific locations around a vessel. There are now a number of new results available for this purpose, including disturbed sea surface Z and sea surface clearance, and sea velocity and acceleration, both disturbed and undisturbed. There is also an air gap result, which I will talk more about in a moment. As an example, here are some comparative results for this vessel which includes sea state disturbance. The lower left result is the undisturbed sea surface Z at position 0, -50, 10, an upstream point. The upper left result is the disturbed sea surface Z at the same point. Note the peak value for disturbed sea surface Z is greater due to reflection from the body. Finally, the upper right result is the disturbed sea surface Z at position 0, 50, 10, a downstream point. You can clearly see the lower peak value, which is an effect of shielding. As I mentioned earlier, one of the new results variables for vessels is the air gap. This is essentially sea surface clearance at a specific point, but with an additional scaling factor. Whilst this could have been created with a post-processing script or user-defined result, we felt it would be useful to a significant number of users, so decided to implement it as a standard result. But what about the scenario where you need to report the air gap from multiple points? Again, a post-processing script could have been used. However, we have introduced a new air gap report to deal with this. The first part of the air gap report is specifying the necessary reporting points, and to do this you need to select the new air gap page on the vessel data form. Here you list the required reporting points and their associated scaling factor. Once this is done, you need to go to the results form and select the air gap report option. The report gives the minimum air gap at each point and the time at which it occurred. Within the report we have two tables, one in order of increasing air gap, the other in order of data input. As usual, these are just the headlines. For an exhaustive list of enhancements in OrcaFlex 11, take a look at the What's New section of the help file. Thanks for watching.